morning. This work is part of my master degree research, and it was developed in collaboration with Professora Déborah Oliveira from University of Brasília, Professor Venicius from Catholic University of Rio de Janeiro, and my advisor, Professor José Araújo. Well, this research deals with fatigue failures in components with small defects. These defects is kind of pores, non-metallic inclusions, scratches, and also in specific, we are dealing with some fatigue failures that occur in crankshaft axis of thermoelectric power plants. In this image, oops. In this image, you can see uncracking emanate from a roll in the crankshaft, and it was made with 4140 steel and 4340. It has 7 meters long and it weighs about 6 tons. The cost of manufacture of one crankshaft is about 6,000 euros, and so the failures of this kind generates expensive costs in the industry. So only contextualization, we have also performed recent work that deals with this thematic in research, and where we analyze the non-metallic inclusions in this material. And we combine the multiaxial critical plane approach with the parameter square root of area to predict the fatigue limit of this material. In this work now, we are introducing artificially manufactured small defects in the samples of the 4140 steel taken from that crankshaft which fails, and also coupling with the Finlay and the MWC multiaxial models in order to estimate the fatigue limit of this material, the multiaxial fatigue limit of this material. So the parameter square root of area was proposed by Murakami, and it was being applied for several decades to estimate the uniaxial fatigue limit of metals. It's only need the harder weakness and the square root of area to estimate the fatigue limit in uniaxial and in torsional loading conditions. This square root of area was the projection of the defect in a plane perpendicular to the maximum principal stress. So our proposal is to calibrate the multiaxial fatigue models to obtain these constants using the limits obtained by the square root of area parameter, instead of using the experimental one obtained. The advantage of using this approach is the simplicity of calibrating these models, because we don't need to perform any experimental tests to obtain the constants to use in these multiaxial fatigue models. So to validate our proposal, we perform an experimental camping with specimens with this geometry, and we introduced a small roll of diameter and height of 1550 micrometers. The materials parameters are there, yield stress of 710 megapascal, 900 megapascal of tensile strength, elongation of 20%, and the Vickers hardness we measured and obtained 320. Uh, all the fatigue tests were performed with sine waves and loading ratio of -1. We conduct tests in phase and 9 degrees out of phase with loading ratios of 0, 0.5, 1, and 2, and infinite. That means pure torsion and uniaxial loads too. Our test was conducted in force control with sine waves. The fatigue test was conducted in these hydraulic test systems. This one able to apply torsional and axial combined loadings, and this one only axial loadings. The fatigue limits obtained by the square root of area parameter was of 220 megapascal in traction compression and 182 in torsion. The square root of area for the defect produced was obtained of 550 in the longitudinal direction, perpendicular to the axis of the specimens, and the projection of in the square root of the projection of the area of the defect in a 45 degrees, which means the plane of the principal, the plane perpendicular to the principal stress in torsional loading was of 1618 micrometers. Oh, calibrating the Findlay model with the values obtained by the square root of area parameter, we obtain this line, this full line. The dashed line represents an error of 20%, and the experimental results, the full marks represent the failures, and the empty marks represent the runouts. For the in-phase tests, the predictions are in more accuracy. Otherwise, the out-of-phase data is more distant for the predictions. The same comparison was made with the MWCM model, and we obtained the same relation with the Findlay. In the tests in phase, the prediction was more accuracy. Otherwise, the out of phase data is more distant for the prediction. We make we calculate the error index of the predictions and the experimental points, and obtain that the MWCM's model provide better results in the in-phase loading conditions, in out-of-phase loading conditions too. The Findlay model provide the worst predictions in the out-of-phase loading conditions. So the main conclusions of our work is that it's possible to calibrate critical plane multiaxial fatigue models with the fatigue limits obtained for the square root of area parameter, and its main advantage is that the calibration not requires any experimental test, and the results provide the error node. The worst error of 39% for the stress ratio of -1. And I already talked about that. For finally, some fracture surface of the specimens we conduct. This one for push-pull tests, only uniaxial. The critical plane approach that we used predicts some planes on where the fracture will be to take. So, but we observed that because of the micro defect insert, this plane was not in accordance. Here, it was to be a fracture in a plane in 45 degrees, which means the plane of maximum maximum shear stress in attraction compression, but the failure occurred in a plane 90 degrees with the perpendicular axis, which means a plane with the maximum principal stress. And the same occur in the test with poor torsion, where a fracture occurs in a plane 45 degrees, what also means the plane perpendicular to the maximum principal directions. And thanks for listening.